geometric optics. I'm not going to change my tone of voice because people are trying to talk over me. We're going to pick back up with geometric optics today. You'll recall that I gave you two important laws. One was the law of reflection. The other one is the law of refraction, which is sometimes called Snell's law. As with the other important law in optics that I just mentioned, Snell's law has two parts to it. One part is about what plane everything happens in. Basically says incident and reflected. This one's kind of parenthetical, but incident, reflected, refracted, and normal are all in the same plane. Okay, the second part to it, as with the other law, the second part is the part that most people actually remember, is the sort of mathematical equation to it, which essentially says that the refractive index for the first medium times the sine of the angle incident from the first medium, and then the refractive index in the second medium and the sine of the angle in the second medium, those products should be equal. So if we draw this thing out, this line represents your interface between, or your boundary between two media. So this one right here has one refractive index, this one right here has another refractive index. We need to draw for ourselves one normal line, which is this dashed line, so it's perpendicular to this interface. We have incident array like this, so this would be theta 1. Now what's going to happen is it hits this interface, some of it gets reflected. So this one right here also would be equal to theta 1. That's law of reflection, and that's this part right here. Some will be refracted. That means it's going to pass through the interface and it's actually going to bend. Like this. And so here's your theta 2. All right, if it was not refracted, it basically would have continued off along this path right here. So you see it bends at this interface. This one right here should go along here if there is no refraction, but because there's refraction, it bends at this point. Now, there's a number of things that result from this. One of them is, and I think I have a picture on here somewhere of it. Oops. One of them is that if the refractive index is different at different wavelengths, then the light will actually spread out at the interface. And so, for example, this right here shows sort of like a cartoon of a diamond and what happens in diamond. It turns out that the refractive index is not the same for all wavelengths of light. Now, wavelength corresponds basically to color for light. So we saw that when we talked about the just properties of waves. So red has a short wavelength, red has a long wavelength, violet has a short wavelength. And so the refractive index is different for each one of these. It basically means you send white light in, it refracts, and it splits. And so it makes sort of like a rainbow effect. Now with diamond, you have all these different faucets, and so that rainbow effect actually kind of manifests as like a glittering or sparkling, if you will. But if you have just a plain prism, that effect can actually manifest by making sort of like a rainbow come out the other side. Another thing that results from this is that if you design a material like a piece of glass and you give it some curvature, you can use it to focus or defocus light and actually create images or re-image an object. That's how everything from a magnifying glass to a telescope to a microscope to your eyeglasses or your contact lenses will work. Third effect is that you can create a sort of optical illusion from this. And your book certainly has a picture somewhere of it. I forget whether it's the bent pencil or whether it's the guy in the swimming pool. But basically, if you look at a glass of water, for example, a glass of water, water level maybe is here. You take a pencil or straw or some such thing. You put it into the glass of water. In actuality, what it does is it just rests in the water like this. But what you will see because of this refraction is that at the surface of the water, the pencil appears to bend like this. So it appears bent if looked at from the side. Now I think towards the end of Monday's class, I talked a little bit about why is it that light refracts as it goes from one medium to another. And that's where I introduced this term N, which is the refractive index, or index of refraction. And I did, in fact, show you at that time this table of values. So these are refractive indices for different media, different common media. So what is it that the refractive index actually measures? It actually tells you how quickly does an electromagnetic wave, which includes light, propagate through the medium. Specifically, your refractive index, for example, N1, is defined as speed of light in vacuum divided by speed of light in the medium in question. So for water, where N is 1.33, it tells us that the speed of light through water is such that C naught divided by C water is 1.33. Or in other words, if you want to get the speed of light in water, you have to divide the speed of light in vacuum by 1.33. So this equation, we can multiply both sides by this. You get C naught is 1.33 times C water. And therefore, C for water is C naught divided by 1.33. C naught, speed of light in vacuum, is one of those numbers that you should have either memorized or written down in a very convenient place to locate quickly, because I expect you to know it when you're doing stuff like quizzes and homeworks and tests without having to ask what it is. If you've forgotten it, it's roughly 3 times 10 to the 8 meters per second. And then we divide it by 1.33. So at this point, it's a calculator problem. We used to have a calculator up here, but it seems to have disappeared, so I'll use this one. You plug it into your calculator, you get about 2.26 times 10 to the 8. So that's how fast light, roughly how fast light travels through water. Now, about this different refractive indices phenomenon, the splitting of light into different colors. What that's all about is this number right here basically represents, to three significant figures, what the speed of light at a particular wavelength is. The standard wavelength that they use actually is sort of yellow. I think it's 580 nanometers is the standard. So if you go to shorter wavelengths, in other words, you look at, say, green at 532 nanometers, or blue at 400 nanometers, or violet at 380 nanometers, what you'll find is that each of those shorter wavelengths travels just a little slower. And if you go to longer wavelengths, maybe you go to red in the 700 nanometer range, for example, or orange at this 590 nanometer range, you'll find that those travel just a little bit faster through water. So this property of having different wavelengths travel at different speeds is sometimes called dispersion. And dispersion is what causes things like rainbows to form. So how does a rainbow, like a natural rainbow, actually form? Does anybody know?
Is it light refracting off of water particles in the sky?
Yeah, usually off of substantial enough water particles to notice some difference, usually like a raindrop or cloud, vapor, this kind of thing. And it is refraction. What basically happens, there's actually a second thing that happens besides refraction, which involves reflection of light. But basically, they pass through this interface. This interface is curved, like this. Your raindrop has some curvature to it. But light enters like this, and it basically splits like this. And it turns out that this one right here tends to be red. This one tends to be purple. And you just go from red to purple through the colors of the rainbow here. Now, you may notice if you actually look at a rainbow, that rainbows always tend to have the same ordering of colors. Has anybody actually taken the time to look at a rainbow and see what order they come in from bottom to top? What's that? Yeah, it is in those orders, but which one's on the bottom? Red or purple? Okay, let's see if I have a picture of a rainbow on here. I may have to open up a different set of notes to get to it a little more convenient. This set. So here's your standard rainbow. Purple on the bottom, red at the top. But you'll notice that it's showing two different drops on this rainbow picture. And it turns out you need more than two, but two gets you how you see red where you see it and how you see purple where you see it. Because looking at this right here, this one should be red, this one should be purple. Yeah, okay. But if you look at what angles stuff comes out at, this means that red should actually come out of the drop lower than purple does. So the colors that we see in the rainbow are sort of reversed from the actual order that they leave from the droplet of water. Why is that? Well, it's because what's happening is, since purple is leaving the drop, let's say, parallel to the ground, and red is leaving the drop at some angle relative to the ground, it means that the red light actually arrives to your eye from a higher up droplet, because the droplet has to be up here in order to come at an angle and reach your eye. Whereas a purple drop maybe has to be here in order to come straight out and reach your eye. And so you see purple at the bottom and red at the top because of this. And all the others in between. Now, if you really enjoy going out on these sort of post-rain, fresh sunshine type days that you get the rainbows, you might be so lucky as to see a double rainbow. What happens with a double rainbow? What order do the colors go in for the second rainbow? Any ideas? They flip. So if you go out and you see just a plain old single rainbow, you get purple to red. Double rainbow, the next one you see, red to purple. Why does it do that? Well, that second rainbow basically is formed for similar reasons to the first one, but it requires an additional reflection. Basically what you're seeing is that there can be more than one reflection inside of a water droplet. All right, and that second reflection basically reverses the color order for you. You may notice something, by the way, about this drawing that is, maybe you've noticed this, maybe you didn't. Maybe you didn't notice it, but your brain did. I don't know. You see that the sunlight comes in, you see that the colors split, and then it shows reflection going on here. It doesn't really show anything coming out the back end of the water drop. Why is that? Why doesn't any of the light come out the back end of the water drop? This is related to the demo that I did in class on Monday, where I took the prism and I rotated it, and you guys watched the little red laser beam basically go across the wall and then vanish at some point. Why did it vanish at some point? And can we figure out when it vanishes? To do that, we need to do a little bit of math. In other words, we need to work with Snell's law a little bit. Okay, Snell's law predicts that some product that involves a sign equals some other product that involves a sign. So if we wanted to find the actual angles, how would we go about doing that? Well, okay, maybe you know the incident angle. Maybe you know the two refractive indices. So you want to solve for the refracted angle. So rearranging this equation would give us sine of theta 2 is equal to n1 over n2 sine of theta 1. All right, so let's test this thing out a little bit. Let's go back to our set of refractive indices, which are shown here. Let's pretend, let's pretend that we have water, for example, that we want to be incident on. So if this is the case, maybe this one right here is air, and this one right here is water. In other words, we're looking at a beam of light or a ray of light that's already in the water and it's approaching the surface of the air and it's going to refract into the air. We want to know what angle does it refract at. All right, so we need to know what angle is it incident on before we do that. All right, so this ratio right here, by the way, would be 1.33 divided by 1.00 because we have the refractive indices of the two. Let's say that we're incident at an angle of 10 degrees. What would our angle of refraction be? Okay, so we need to pull out the calculators again. Actually, instead of using this calculator, what if I use the one that's built into the computer, just for variety's sake. Nope. Thanks, IT. This must be the only computer that I've ever touched that the calculator app doesn't work on for some bizarre reason. So this is a little less interesting, but okay, we'll plug it in here. Sine of 10 degrees. So sine of 10 degrees, and my calculator says that that is 0.174. And then we have to multiply it by 1.33. So this is 1.33 times 0.174. What I get is 0.230. No, 0.231. Okay. So what is the angle that it leaves the water and enters the air at? Well, we just found that the sine of the angle is 0.231. So if we know what the sine of the angle is and we want to find what the angle is, we have to use the arc sine button on the calculator. That's the one that says sine -1. Usually that's a second, and then the second function button, and then the sine button. So when I put all that in, I get 13.4 degrees. Okay, that tells us that it should be leaving at 13.4 degrees, a little bit bigger than the angle that it entered the water at. For the sake of some practice for you guys, let's do this same problem again. I'm going to make a little quiz out of it. And I'm going to change what the angle of incidence is. So we just did a really small angle of incidence, 10 degrees. Let's do a big angle of incidence. So we'll make it theta 1, 80 degrees, for example. What we want to know is, what will theta 2 be? And here, I'll even type it on here so that we can have it open while you're entering it. Short answer so that you can enter a number or word. Important question there. So light is incident from water, and that's N equals 1.33, to air, that's N equals 1.00. At an angle of, I said 80 degrees, right? 80 degrees. Let's see, like this. What will the refracted angle? There we go. So let's take maybe 3 or 4 minutes to calculate what the refracted angle is. Have you worked it out yet? Curious to see because you should get as your answer. Sine of 80 times 1.33. Uh-oh. Now you gotta take the arc sine of that number. Uh-oh. Go ahead and close it down. Okay.
5 seconds.
All right. Put in your answer. Even if it's wrong, it's still better than nothing. Okay. Close it now. Almost everybody did it. That's a lot of digits. That's a lot of digits, something. Don't know. Don't know. Does not exist. Okay. Does not in A. All right. So we'll take it. Huh. Wasn't a number, was it?
No, because there was, you can't do the inverse sine of a number that's bigger than 1.
That's right. The possible numbers that you can take an inverse sine and get an actual number for range from -1 to +1. So if you get a number that's bigger than 1 or smaller than -1, then you're just going to get an error or not a number or some such thing out of your calculator when you go to take the inverse sine. If you look at what all goes into this, right now we basically have that sine theta 2 should be 1.33 divided by 1 times sine of 80. And if memory serves, this comes out to something like 1.3 or something like that.
1.31005.
1.31. Only need 3 sig figs. Okay, so this is saying basically that somehow theta 2 has to be the inverse sine of 1.31. If you put that into your calculator should spit out an error message, because there is no number that gives you that if you take the sine of it, you get something bigger than 1. So it's not a number. But the math is all correct up to there. We didn't do anything funny with the math. So what does that mean should happen? We basically hit some weird error in the calculator. The weird error actually tells us something physically is going to happen. Basically what it says is there isn't any angle that you can refract the light at, therefore the light won't refract. So where does the light go? Well, look back at our diagram, you'll see that there's actually 3 rays drawn here. So here's your incident ray. It's coming in like this. This would be your refracted ray. This one right here is a reflected ray. Basically what happens is if you get not a number at this interface, in other words, if your incident angle is too big, then all of the light is reflected from the interface. There's no refraction into the outside. Okay? Now, how big of an angle is it that you can go into at this interface and still have it refract? Well, basically, to answer that question, you come back to Snell's law and you say, I want to solve for the maximum possible angle here. Well, the maximum possible angle is the one where theta 2 refracts at 90 degrees. So if theta 2 is 90, then the sine of theta 2 is what? Anybody remember what the sine of 90 degrees is? It's a 1. So what you do is you solve for this angle, theta 1. And now instead of being 1.33 over 1.00, it becomes 1.00 over 1.33 because we're solving for the other angle now. And you use sine of 90 degrees. All right, so this ends up looking like whatever 1 over 1.3 is. And when you plug that into your calculator, you get the maximum angle that will give you refraction. It tells you beyond this angle, no refraction occurs. So let's plug it in here. What I get is 48.75 degrees, about 48.8 degrees. Any larger angle and you get total internal reflection. Basically means all the light is reflected from that interface. It doesn't necessarily mean, by the way, that the material absorbs the light. In fact, having total internal reflection is quite useful to us. There is some loss because sometimes you do absorb light or scatter or whatever. But this is what is the basis of all of our modern telecommunications industry is based on this. Because most of our modern telecommunications uses fiber. For example, we, in the last few years, upgraded the infrastructure, like a Troy Cable upgraded its infrastructure. And now you have fiber internet rather than a literal coaxial cable. The way that that works is that you have these optical fibers. The optical fibers are designed in such a way that you send your signal in one end. And it bounces off for total internal reflection, it bounces off for total internal reflection, and so on. Until you get to the other end. And then it basically can come out. I guess I should probably draw it as actually refracting somewhat at the output. So, okay, so fiber optics actually makes use of this total internal reflection phenomenon. Going back to the picture that I showed earlier today with the water drops, I showed that light seems to go in and then it doesn't come out the other side. What that implies is that it's coming in at just the right angle, or bigger than the right angle, to get total internal reflection. So there is no output light because the angle of incidence is too big. Furthermore, going to the example we did in class, we found that at some point the angle got big enough that light would no longer refract through the back end of the prism. That's why when I turned the little table, the laser beam basically swept along and then somewhere over here it just vanishes. What basically has happened is I've passed through beyond the angle of total internal reflection. There's no longer a refracted ray, only a reflected ray. There's one other thing to say about refraction as such and how it interacts with light, which is that light itself carries both energy and momentum. All right. If you want to figure out how much energy is carried by a single wave packet of light, you use this thing called the Plancks constant, and you multiply it by the frequency of the light. So in vacuum, what does that look like? E should look like H times F, which looks like H times, if we look over here, that would be the C over lambda term. Sometimes called HC naught over lambda naught. Okay, and the units for that end up being energy. It ends up being a very small number in joules. This is times 10 to the minus 34, by the way, this Planck's constant is. So F, for what it's worth, is usually for visible light is of order 10 to the plus 14 hertz. You multiply that by something that's 10 to the minus 34, you still end up with something that's 10 to the minus 20. And actually, when you combine the leading terms, the argument, 6.26, and the leading argument on the frequency, you actually end up with something times 10 to the minus 19 for what that's worth. So very small energy per photon. However, if you have lots and lots of photons, then collectively you have a lot of energy. So a high power laser just has many, many photons in it, is the upshot of that. Now, where I'm going with this is, when you pass light into another medium from vacuum, energy needs to be conserved. The energy of the light has to be conserved. Now, the speed of the light changes. We already know that because that's what the point of the refractive index is. The speed of the light has changed. This means that we need to have the wavelength change in order for the frequency to remain unchanged, because the energy is this product right here. H never changes. So when you pass from one medium to another, you actually change the wavelength as well as the speed of the light, but the frequency does not change. All right. Back to Snell's law. I guess the last thing, which is, and I brought this up last time, but I want to reiterate it. Why does light bend at an interface? And the answer is because light travels in what's called wavefronts. And when a wavefront hits a given interface, the wavefront itself attempts to stay together. Why does the wavefront try to stay together? That's pretty complicated. It has to do with what's called Huygens principle. It's named after Christian Huygens, who was a contemporary of Isaac Newton. Now, Newton and Huygens had their own theories, or were proponents of their own theories as to what light was. What is the nature of light? Newton liked to think of light as being essentially particles. I think he called them light corpuscles. Basically means little particles of light. So his theory was that light is just a particle, and it behaves as just a particle. This guy, Christian Huygens, said, no, light is not a particle. Light is a wave. It behaves fundamentally as a wave. So which one was right? Was it Huygens or Newton? Well, at their day, at the time of Newton and Huygens, there wasn't any way to really resolve between the two. Nobody could really definitively say one way or the other. Then, at the turn of the 19th century, so around the year 1800, a set of experiments were done on light that seemed to indicate that it was in fact a wave. We'll talk about those experiments later in this chapter. The main one is what's called Young's double slit experiment. And he found that light has some wave-like properties. Specifically, it can interfere just as waves do. However, that was not the end of the argument, because then in the early 20th century, we got Einstein. And Einstein was able to show, and for this he actually won the Nobel Prize, he was able to show that light also has a particle nature to it. And he did that by explaining a thing called the photoelectric effect. Photoelectric effect, you basically take a metal, you shine some light on it, and what happens is you get a current. You get charges moving around in the metal. And it turns out that how much energy the charges have depends on the energy only of the photons of the light. In other words, only on this product here. And for light of a low enough frequency, you don't get any charges at all. There is no photoelectric effect observed if the frequency is too low. So back to Huygens' principle. Huygens' principle basically says that if you want to figure out how light moves or how light behaves, you look at a wavefront. And that wavefront can be approximated by considering a bunch of little wavelets. And basically looking at how these little wavelets interfere with each other. So that if your initial wavefront is a plane shape like this, then the new wavefront sometime later should look like the interference of all these little wavelets, which is basically the envelope equation, or something that's drawn more or less tangent to the wavelets, which you see is another plane wave. So what you end up getting is plane wave after plane wave after plane wave. This basically defines a beam of light, as we draw right here. But when it interacts with a surface, an interface, little charges inside of that interface also radiate some light, which in turn interferes with your initial light. And that's A, why the light slows down when it enters the new medium, or speeds up, depending. And B, it's also why this thing will bend at the interface. Because when the first part enters it, suddenly you get interference at that point, but there is nothing over here yet, so there's no interference yet. And then as this part starts to enter, there starts to be interference, and basically the whole wave slows down as it enters. And that's what causes the bending of light, and that's what causes for us Snell's law. I think that we have to quit on that note.